Did the audio from
Sure.
yeah.
Welcome everyone to this week's talk by Redi Haderi from London-based University. And today he will give us a talk about two models for higher operads. So it's all yours. Ready?
Yes, right. So thank you for the invitation and my apologies for the really misunderstanding. Uh, for some reason, I just assumed the talk is on Wednesday and didn't even check, even though the email said so. So again, my apologies. So Akif, we have about until 10 o'clock, I suppose.
Yeah. Yes.
Yes, okay. So yes, my so today then I'll be briefer than I initially planned. So we will talk about two models for infinity operads. And so number one, I will describe what is a Lure infinity operad. And number two, I will describe another model which we call list infinity operad. So the talk is like mostly expository. Uh, and let's get started. So we will mostly be dealing with the combinatorial nature of these models. So I'm not gonna like talk about like all examples of operads and how and why do we need, etc., etc. Except for briefly, and I want to focus on some the combinatorial features of these theories because I think it's a very interesting thing to discuss, as we will see hopefully in the brief amount of time we have at our disposal. So let me, so because I want to do like a combinatorics focused uh, talk, so let me start by uh, expressing an idea. So we have the notion of category, and in a category we have objects, say A, B, C, etc. And then we have morphisms, which we typically denote by arrows, sorry, F, A to B. So this is an arrow, and an alternative popular way to actually depict morphisms is what we call string diagrammatic. So F, so we think of this A and B as sort of being these strings like input and output, and F as being a sort of operation you perform with input A and output B. So this is called, so this we can say is a string diagrammatic uh, representation of a morphism. And so when we talk about, say, composition, so arrow theoretically, we kind of depict like, so we have morphism F, morphism G, then we do the composite, and we think of this as a little too simplex if we want to use this language. String diagrammatically, we kind of do this. So we have F and G composable, meaning they sort of can be concatenated like this. Then we apply the composition operation and we get a new operation, G composed with F. A to C. So uh, this is sort of, we crush this middle part that I depicted in red. We sort of squash it and we get this composite operation. And so this string diagrammatic sort of notation, so this string diagrammatic idea is particularly so useful for monoidal categories and algebra. So let me just briefly say what I mean by this. So monoidal category is a category V plus sort of uh, a multiplication operation, V times V to V, unital, whatever, appropriately weakly, etc., etc. But the point is that uh, so if I have two morphisms uh, in a monoidal category, I can like multiply them to get like a new one.
Uh, can I interrupt and ask something now, or should I wait till the
Yes,
end?
no, ask.
Uh, I was wondering if, in the string diagram,
Mm-hmm.
we could conceive of composition itself as a box with two inputs F and G and one output G composition F.
Uh,
And is
that
that point of view pursued?
yes, I can say something. So basically, uh, this idea can be realized if we consider an operad whose algebras are basically categories or enriched categories. Time permitting in the end, if you don't mind, I can
Hmm.
clarify the point and
Okay.
maybe it will satisfy uh, your your curiosity. Okay,
Hmm.
right?
Thank you.
Yeah, but remind me though, because I could forget. Because
Hmm.
I'm kind of in a rush because what I have to
Yeah,
cover.
I understand. Yeah.
Yeah. So the reason I'm in a rush is because what I have to cover is a little bit involved, but at the same time, I'm trying to motivate the subject as much as possible.
Yeah,
Yeah,
yeah.
so in a monoidal category, we can like multiply arrows like this. So you can think of Cartesian products, for example. We want to do algebra with them, like sets and products. You can keep that in mind. That's totally fine. So string diagrammatically, uh, so let me maybe just write it like this. So string diagrammatically, this would be just writing these strings side by side. That signifies sort of. So the people in applied category theory like to use the word like parallel processing of operations, for example, things of that form. That is encoded by like a monoidal structure, etc. Uh, but so the reason I also mention algebra, and so we would like to kind of do algebra in monoidal categories, for example. That's just one corner of examples of a much more general idea, but just to motivate sort of. So consider, for instance, the notion of monoid in a monoidal category V. So ideally, what we want, and I will draw this in string diagrammatic form, is that we have like a multiplication operation. So monoid in V, and let's say an object A in V is a monoid. means we have this operation. So this is multiplication. And we have a unit which, so whatever U. So operation with no inputs means from the unit of the monoidal structure. For sets, it's just the one object set which picks the identity element. So this is unit. And for example, how do we think about associativity? In a very simple way. So we do a multiplication. Oops, came out awkward. So if I do a multiplication like this and then again multiply, this should be the same as just, let me do it backwards this time. So I do a multiplication here. So these strings are all A, and A. So this is associativity. And similarly for unitality, let me not draw that. You can probably guess. So the point is that having these diagrams, especially, for example, things of more complicated nature like that, is useful in doing algebra, okay, and expressing algebraic ideas. So the simplest example here is a monoid. And so the notion of operad really encodes a way for us to do this. So let me very briefly discuss what is an operad. So this is, I guess, the definition. So an operad P consists of, so we have objects just like in a category, except we call them colors for purely traditional reasons. Okay, so colors, A, B, C, etc. And we have, instead of morphisms, we have operations which have source like a sequence of colors, say A1 to AN, and target another color B. Now, of course, these operations are better understood in string diagrammatic terms. So A1 up to AN into B. And then we have identities. So which we can denote either identity from A to A, but usually we just draw a straight string, meaning nothing is happening. It's really identity. And we have composition, meaning, so I will just draw a picture. So if I have some operation, G, say from some B1 up to, I don't know, BL, and these are themselves outputs of some operations. They sequence A1 up to sequence AL. I'm underlying meanings. There is a sequence, not just a mere object. So let's say this is F1 until FL. So these sort of compose to give G composed with F underline, meaning the sequence. And these are like, let's say, all the A's you can imagine, like you just you just sort of concatenate all the inputs and output C. Okay, so and this composition is, of course, required to be associative, and unital. So this is the type of structure that an operand encodes. So for examples, so there are many famous examples. So for example, the associative operand. So this has a single color and single operation. So let's call this color whatever, dot. So from any sequence of whatever length to this single color. So this is the terminal. So this is the terminal operand. And so because of time restrictions, I'm going to give just one more example. So V monoidal category. So there is an operand V tensor, which means operand structure on V given by the monoidal operation. So this has as colors objects of V and operations. So as you can imagine at this point, I suppose, so an operation from a sequence of objects A1 to ALN to B are just morphisms A1 times AN into B. So you can think of like, so imagine these are sets, for instance, with the Cartesian product. This F would be some sort of multiplication, which assigns to an n tuple, so one element for each AI, an element of B. So this is like really encoding some sort of, operation that we want to perform. And so, we have a notion of an algebra. So a P algebra in V is a morphism or an action, whatever you want to call it, from P into V tensor. So basically, you have some monoidal category of interest, say, and you have your operand encoding some kind of operations and composition between them. So an algebra assigns to colors of the operand objects in your monoidal category and to operations in your operand sort of a realization in the monoidal category. So it encodes like an algebraic structure. And so I apologize for the lack of examples due to time, but so a monoid in V is an algebra of the associative operand. Great. I mean, so what I described here is what is called in the literature non-symmetric operand or planar operads. So we could have extra structure where we can permute inputs of operations. So I'm going to restrict myself to this case for simplicity, really, and because the work I want to describe later is developed just in the non-symmetric case. But there are, as you can see, interesting examples already, monoids. Okay, so for example, suppose V. Okay, so let me use this associative algebra example to motivate sort of higher operand. So what is a theory of higher operads supposed to achieve is that suppose uh, suppose for some reason uh, so let's put it like this. So for example, suppose you want to talk about monoidal categories somehow as algebras. And these are supposed to be associative algebras in the 2-1 category of categories. So the problem is if you follow the definition I just gave of algebra, you get a strict monoidal category. And what you want is like a notion of weak associative algebra. And if you want to talk about, say, monoidal infinity category, so suppose you want to do that for some reason, you want to say this is associative algebra in the infinity category of infinity categories. So this would be much more involved, of course, but still, you would want to talk about homotopy coherent algebra, not just like a strict algebra, like a one categorical sort of notion. So, of course, this is the simplest type of example where I just took one operad and look, it already got us some interesting ideas in mind, like monoidal infinity categories. So there are algebras, so there are operads controlling all sorts of objects people are interested in. I'll just say them in words. There are whole books on the subject, of course. So there are, for example, operads for commutative algebras, if you include symmetries, operads for Lie algebras. So there are operads for loop spaces in algebraic topology where the subject actually originated from. So what else? So there is operads for enrichment of categories, which is one of my favorite examples, etc., etc., etc. So all these structures have homotopy coherent variants that are of interest. And so we are interested in notion of infinity operad. Okay, so now I will sort of describe, I will jump and describe Floor infinity operads. And I will have to be terse, and I will have to be somewhat brief, but I hope the pictures so this is basically about encoding, so if we go back, so we have this sort of composition scheme, operations with inputs. Now we want to sort of have these, but where they compose up to coherent homotopy, basically, right? And so Lurie, in his book Higher Algebra, developed a model for these. I will describe the non-symmetric variant. Lurie has the symmetric variant. So let me so first of all, we need to define a category. So we'll define so the combinatorial framework. So there is a category. Well, so delta is the usual, finite ordinals order preserving maps that we use for simplicial sets. I take its opposite and I want to call it something else, which is the interval category, because I get confused as hell thinking about delta op. Okay, so if you want my advice, you forget about that for a second. So this has as objects finite ordered sets, and as morphisms, order preserving maps, order plus endpoint, let's put it like this, preserving maps. And so let me describe the imagery corresponding to these to this category and what it encodes. So basically, so we think of an object. So finite ordered set. Let me use this space here. I'm gonna think about it as, so because we are interested in distinguishing the first and the last element, basically, I'm gonna think about it as having a least element, which I will call minus, then it has some finite amount of elements, A1 to AL, and another like maximal element, which I will denote plus. So when I do this like bracket notation, basically, I have my A here, which is an ordered set consisting of the elements inside, and I produce this by adding the two endpoints. So the way and the picture here is that this ordered set A, I will write it as a bunch of strings, A1, A2, up to AL. So now what is a map from A to B? So let's say I have some B's here, whatever, don't matter. So I will think as the elements minus and plus and sort of invisible, in the background. They don't really play a role which is substantial. But the thing is that some of the A's on the left can map to the minus, so I will leave them alone. And some of the A's will map into B's. So for instance, some of these A's, so A1, A2, let's say map to B1, and then nothing maps into B2, and let's say this one maps here, I don't know, something like this. So the point is that this map phi here creates like this relationship, like a bunch of these trees that we saw. And so this is like a bunch of operatic operations. And so we can form something called the category of operators. So P operad, and the category of operators, which we denote, oh, there is a conflict of notation. This has nothing to do with the V tensor. I'm so sorry. Both notations are standard in the literature. Sorry about that. So this category of operators is a construction due to Peter May and Thompson. So this is a classical operatic construction. So this has as objects sequences of colors in P and as morphisms. Okay, so I have a sequence of colors A1, AL, I'm going to kind of think about it as an element of this sort of finite ordered sets category that I described here to B1, whatever, BK. So this consists of, so this has two components. So a map, let me call it phi, from A to B, where sort of A and B are like the sets of the same size as these sequences. I hope you can imagine, and I'm not confusing you. And for each, so this is number one, number two, for each I between 1 and K, an operation so let's say Fi from phi inverse Bi in A to Bi. I'm kind of abusing notation, but I hope the idea is clear. So let me do an example. So let's say I have my operad and an operation between sequence A1, A2, A3, A4, let's say A5 into, let's say B1, B2, and B3 is something like this. So you pick like some operation here, F1, some operation here, F2, and some operation here, F3. And so the map between ordered sets, which classifies this type of morphism, is the one that maps this to the element minus and this to the element plus, and of course, A2, A3, they are sort of mapped into B, A4 is mapped into B3, and there is nothing mapping into B2, so we get an operation with no inputs on B2. So this is a general idea, so I hope at least at the level of image this is clear. So we have the functor from operads into categories which are equipped with a functor into this category that we created previously. Now, so this is P tensor. And this P tensor is equipped with a map which we call pi into this interval category that I described. Anyway, so Lurie's idea is that we can detect these. So, I'm out of time. Okay, so Lurie's recognition theorem so says the following. So a category or let's say, sorry about that. So let pi from a category C into this nice combinatorial stuff interval category here. So be here. And so the point is what type of properties this satisfies so that it's coming from an operad. So we have that. I'm writing in horrible fashion, but C is equivalent to some P tensor for P some operad if so now I have to okay, race against time. Okay, so for each what are these called? Inert morphism. I will explain what this is in a second. So let's call this eta. So this is the sequence with n elements into one. And a in the pre-image. So there is a pi co-Cartesian lift in C, say, yes. This so basically this inert, I will just explain it with a picture. So inert is where everything in the codomain, so everything maps like so there is no multiple inputs on any operation. It's a picture like this. And yeah. So then sorry, this should be, there's a mistake, not to one here. This is a general one. N to K, so from N elements to K elements. So this is inert 4 to 2, what I drew. Okay, so for each inert row I n to 1, I will explain what this is in a second. And so for each inert, so choosing pi co-Cartesian lifts provides an equivalence. What's the equivalence? So from the fiber of C on N to the product I from 1 to N, C of 1. So this row I did I write the row I? Don't matter. So this is where you have, say, 1, 2, 3, and 4, and you kind of map into this single element here. So you pick like the ith term of your sequence and you choose that particular morphism. So this is row 3 from 4 to 1. Anyway, so the third axiom, maybe quick. So this is about mapping spaces. So what does this say? So for each, I have to think. So the problem with Lurie's model is that you kind of have to think about the definition because it's not straightforward. So let me just quickly check reference. Yes. Okay, so if you let any morphism P and M, and so you pick A and Cn, yes, so this is B and Cm, then basically, so there is an induced equivalence from C over this C AB to product I in M, and you take HOMS from basically A restricted to, sorry about the bad notation, I, so let's call it I inverse I, BI. And each BI is like the co-Cartesian lift chosen from the previous one, and these are over phi composed with these row i's. Okay, so what I wrote here is not 100% super well defined, but I think it is clear enough. So the thing is, okay, so moral of the story is that you can sort of characterize what's an operad. So you look at which one of these functors is an operad. And so Lurie's model is based on this idea, and then you define basically an infinity operad here. Pretty much same story. So you take an infinity category over this, and you just replicate this definition, because all these ideas of equivalence, of co-Cartesian, and co-Cartesian, so these all have interpretation in the theory of infinity categories, and you sort of get. So I wanted to, the reason I wanted to start with Lurie and then sort of talk about our work a little is because, as you can see, this is a quite involved combinatorial structure, and it's not straightforward at all. So I thought I would avoid this problem, but I couldn't write the definition without looking at notes, which is a problem. Okay, so maybe some people can, but I've seen other people who actually wrote on the subject who sort of got confused about the definition. Is my point. So I will take 5 more minutes, if you don't mind, to just briefly talk about our work, given that I already wasted that time being late. So the list model. So this is supposed, so people have a desire to find like a model for infinity operads, which is kind of more straightforward and intuitive. Uh, and depending on what you want to do, so there are tons. So there are more models for infinity operads than for infinity categories. Nonetheless, so our idea is that we kind of look for, so we define a category which we call list, and the objects are sets and the morphisms. So I have set A and say set X, and the morphisms I denote it with a slash. These are not functions. Assign to A in A a list of elements, say U of A, x1, xn, in xn for some n. So this is, I mean, if you want to be fancy, the Kleisli category of the free monoid monodon sets. I hate to use this term, but just so people don't accuse me of not being well defined. Anyway, so you from functions on sets, you consider these listings on sets. And so the point is that for infinity category, the combinatorial object that we use to kind of model it is functors delta op to set, which are simplicial sets, plus a property, meaning the quasi-category property. And for infinity operad, you can consider delta op to this list, okay, plus some property. And so this makes the theory fairly simple. As a matter of fact, let me state our definition. Okay. So a list infinity operad is a, well, we call these things simplicial list. Say P, sorry, I'll be done in a minute, delta op to this new category, such that number one, so this is a condition on the nature of operads, meaning that if theta from L to K in delta is such that, so this is a technical condition, theta L is K, so it takes the endpoint to the endpoint. So this implies that the induced map from the set of K simplices to the set of L simplices is a function. And number two, the simplicial set LP, I will say what this is in a second. So this is where, so let me make a little notation here. So for a set X, Lx is the free monoid on X, meaning that this is just a set of finite sequences. And so what I mean by LP here is that you take the free monoid functor on each set of simplices and you get a simplicial set. So this is just the Kleisli functor, and this is an infinity category. And so, yeah, this is our definition. So condition number one is something which is a technical condition, but it makes the theory better. And condition two is fairly simple and is just based on the notion of infinity category. So as you can see, the definition here is simplicial, and combinatorially speaking, there are no fibrations, no stuff like that. And so this is also combinatorially tractable, and there's a lot of intuition behind it, which unfortunately I didn't get to speak much about. But in any case, this is it for my talk. Thanks for listening.
Thank you, Redi. Any questions? Simi, you had a question? Maybe.
Yes, the question was, can we, in the beginning of the talk,
Yes, okay.
composition?
Yeah, okay. So, so let me say here as an answer, categories as algebras. So there is an operad which I mean, there's no standard notation for it, but so I call it like H. Let's call it H. So let's fix a set of objects. Let's say O. So you define this operad HO. So this has colors, pairs, say AB of objects. So these are the intended objects of your category, right? So now you want to define a category with these objects. And as operations, so you say that there is a unique operation, doesn't matter what we denote it. So like this. So you have like A1, A2, A2, A3. So you take pairs where the second coordinate of the first pair is the first coordinate of the second pair, and so on, A3, A4, whatever, until like AN minus 1, AN. And there's unique operation from this into, so let's call this whatever, mu something, into A1, AN. And so what happens is that an HO algebra in any monoidal category V will be equal precisely to a category enriched in V. So, because this algebra, so if you think about it as a morphism, so for each pair AB kind of picks a Hom set. So if we call this algebra C, this picks a Hom set or Hom object. You can think of sets PAB, and these mu's pick up compositions. And so you can really think of like the structure of a category as sort of coming from this operad where you have the morphisms which are concatenated, sort of mapping down and composing into a single one. So I don't know if that's satisfactory.
What role does H0 algebra, the term H0 algebra,
No, it's
or
not
the
H0.
reason of
It's
attaching an
O.
algebra?
No,
Uh,
it's O. O. So O is a fixed set of objects, okay?
yeah.
And HO is an operad
Mhm.
whose colors are pairs of objects.
Mhm.
And it has a single operation, whatever we call it, mu, from
Mhm.
like a sequence of colors. Now it's a sequence of these pairs, and the sequence has to be such that it's of the form, A1, A2, A2, A3, and
And
until
that's
A.
also associative composition, right? You're describing in this case.
So I'm describing what the operad HO is. Okay.
Okay. Mhm.
So it has these colors, which are these pairs, and these operations uh, for each A1, A2, AN. So the operation has input A1, A2, A2, A3 until AN minus 1 AN, these pairs. And as output, it has A1, AN. Now, when you pick an algebra, to each pair AB, you assign like an object in V, and you can think of that as the home object. And if you think about composition, uh, basically, let me do it here. So this will, for instance, let me do it just for two things. So this will assign like a morphism in V from CA1A2 tensor C A2A3 to C A1A3, and you obtain some composition uh, when you take an algebra. Now this goes on like this is somewhat of a long story, but if V is like sets, um, you can do a Grothendieck construction of sorts, and you kind of get that idea that composing morphisms is like composing, uh, multiplying, basically. Uh, and on the infinity categorical front, like if you take homotopy coherent algebras of this, you basically would get like the infinity algebras of this in spaces give you infinity one categories with a fixed set of objects, and infinity algebras in infinity categories would give you like uh, infinity two categories with a set of objects. So it's an interesting opera to consider.
Mhm.
Uh,
Does this have any connection to your combinatorial interests, or has some, I don't
uh,
know.
yeah, I mean, it does because, okay, so this is kind of too much ahead work in pro. So, for example, um, with the simplicial list formalism, um, so you can develop a notion of left vibration, which is appropriate and simple, and sort of, I mean, this is not written anywhere because it's just my own. It will appear, I hope, sometime in the
Mhm.
future in some paper. But so you can take sort of quasi categories and really identify them on the nose with left vibrations over this HO. So let's say quasi categories with fixed set of objects. And you can do this very easily with a combinatorial construction. So the point of having these good combinatorial models is to perform. So think about quasi-categories themselves. You can create these left vibrations, even Cartesian, co-Cartesian vibrations in an easy way, while creating coherent functors is very messy. So similarly for operads, if you have a combinatorially tractable model, the idea is that you can create, for example, these fibrations, which are really algebras. So the idea is to study algebras in the end. We can create these fibrations which are kind of nice, and you can write them down, you know. And so, and you can get results like, I should say this is not a result, this is like conjecture. So let me be very clear. So this is a little niceness conjecture, you know, it's not like something groundbreaking or anything. I'm just saying you can do these things with simplicial lists. With Lewis model, you have to keep track of co-Cartesian fibrations all the lifts all the time. And the model structure as well relies on marked simplicial sets because of that. It makes the theory fairly complex. I check the chat. Nothing.
Okay, thank you. I don't have more questions now, but maybe later.
Yeah, sure.
So if there is no other question, then I can stop the recording.